How about letter number Z?
Letter number D.
Did you say C?
B.
B. Okay.
Oh, I found my homework. It was next to my French battleship notes.
Oh, well, there you go.
Yeah.
Okay, so number 7, you're asked to find the inverse of the function. And number 7 says y equals log base 6 of x plus 2. So what's the first step, Ethan, to find the inverse?
Switch the X and the Y.
Good. Switch x and y. Okay, what's the next step?
Subtract 2.
So if the problem said log base 6 of x minus 2 without parentheses, then yes, you would like take the 2 to the other side, or plus 2 without parentheses. But because there's parentheses around it, those parentheses are keeping that glued together. So it can't be separated from the log because the parentheses are connected with the log. So you can't do anything else with trying to get the equation like by itself. So the log part is by itself. There's no extra adding or subtracting that we have to do to get one thing to the other side. David, what do you think? Right, so the only thing for you to do at this point is to convert it. So like looking at the difference, if it said x plus 2 and there was no parentheses, then you would take this 2 to the other side. But because there are parentheses in this problem, that parentheses attaches all of this together. So the option that you have left would be to convert it into the other form. So David said y plus 2, because that's whatever was after the log, is equal to 6 to the power of x, the base to the x power. Questions? So now, David, what do you do? Now you can subtract the 2, and you get 6 to the x, and then minus 2. And that minus 2 is not part of the exponent. It's just like on the same line or level as the 6. So the inverse, sorry, that's sloppy. There we go. Would be 6 to the x, and then minus 2. So you'll have to look to see like if there's parentheses in the problem, that keeps those things attached together, the x plus 2, it keeps that together. If there's not parentheses, then you would take something to the other side. Same. Yeah. So looking at A, starting exactly the same way, x equals log y divided by 2. Sorry, you can't see it. There we go. So right now, these are attached together. They're connected with the log. They're right next to the log. So you can't move anything to the other side. So instead, Sarah, how would you write it as an exponent? Do you know what the base is? So what would the base be? Yeah. So the base is 10. If it's not written, it's implied to be 10. So even though there's nothing there, that's the common log. And anytime it's a common log, there's a base of 10. So if we write this the same exact way that we did with David's, you're taking the y over 2. That goes on the other side. Now we're getting the equation in exponent form. The base is 10, and then we have the power of x. So y over 2 is equal to 10 to the x. How do you get y by itself? Multiply by 2. Can you multiply those together? Can I take 10 to the x power and multiply it by 2? And make it 20 to the x? No. Why not, Paige?
Oh, because they don't have the same power.
They don't have the same power. They're not the same types of numbers. This is an exponential number with an exponent of x. The 2 is just the number 2. Sure, it could have an exponent of 1, but it's still just the number 2. So you can write it as 2 times 10 to the x You could write it as 2 with 10 in parentheses to the x. But that's the form that we started this chapter out with. That's my y equals ab to the x form, where 2 is the initial value, b is the base or the growth factor, the decay factor. The power is x. So you don't multiply numbers together if they're not the same type of number. So if one is an exponent, the other one isn't, we can't multiply them together. And they have to have the same exponent for us to multiply them together. Other questions? Jenna? So the directions for number 8 want us to use log 4, which is 0.602, and log 7, which is 0.845, to evaluate the logarithm. And right now they give us the log of 64 over 49. So the first thing that you have to think about is you have to change the numbers in order to use either 4, the log of 4 and the log of 7, or one or the other. But somehow we have to take the 64 and the 49 and get them to become into a 4 and a 7. So, Sarah, how could we try and do that?
So it would be log 4 to the third over 7 squared.
Right, so you can change 64 into being 4 cubed. You can change 49 into being 7 squared. So that would be the first step. Rewrite them so that they're as an exponent. And then if you have division, division means what? How can we expand it when you're dealing with logs? Sarah? Subtract it. So we really have log 4 cubed minus log 7 squared. Okay, so we still need to continue on because it's not quite done being expanded. What else do you have to do to expand it? Is that?
Move the exponent to the front.
Right. That's the power property. So if something is being cubed, you're moving that power to the front. So now we have 3 times the log of 4 minus 2 times the log of 7. So this log of 4 becomes 0.602, and the log of 7 becomes 0.845. And then you're plugging that into your calculator and you're getting some number 0.116. So write the numbers as powers, make it division because, or it is division, so it creates a subtraction problem, and then that power property says you move the power to the front to change it to multiplication. Questions on that?
Or no, I have a question for something else.
Yeah.
I don't really need to see the full 9b, but I'm just wondering how
Yeah.
do you...
Now let's go with B, 9b. So number 9, we have negative log base 3 of x, and then it says minus 1. So the first thing that we need to think about would be graphing the exponential equation, and that would just be the base to the power of x, which you should already have the t-chart right next door. So Izza, do you have that t-chart for letter A complete?
Yeah.
What do you have?
Negative 2, 1/9, negative 1, 1/3, 0, 1, 1, 3, 2, 9.
So 0, 1, 1, 3, 2, 9. Okay, so Izza, just kind of talk about how to get an exponent. What do you do if you have an exponent to get a log?
Just flip the numbers.
You flip the numbers. Okay, so I'm going to flip the numbers. This is a 1/9, not a negative. I'm sorry.
Should the 2 be a 9?
Oh, yeah, I said that.
Yeah, I don't know what I wrote. Okay, so we have 1/9, 1/3, 1, 3, 9. And then we have negative 2, negative 1, 0, 1, 2. So that would be what you should have done for letter A. Letter B says negative log base 3 of x. And then, yes, there's a minus 1, but I want you to ignore the minus 1 for right now. So how is that negative going to change this t-chart? What would it do to that t-chart? Virginia?
Would it
-2? So it's not going to flip it. Okay, Ken?
it'll make all the x values equal.
Not the x values. Kate?
Make all the y values
It's going to
negative.
make all the y values negative because the log is the function. The function is your y. So if x was negative, then it would make the x values negative. But the negative is in front of the log, which is in front of the function. The function is the same thing as y. So a function is y, f of x is y. So it's going to make all of these negative. So that means this is now a plus 2, this is a plus 1. Well, 0 is still 0. Now we have a negative 1 and a negative 2. So we're going to graph that. And then we'll talk about what that last part with the plus 1 or the minus 1 means. Sorry, sir. So I'm going to graph these values just like we would graph any other points. So at 1/9 we're at 2. At 1/3 we have 1. 1 is 0. 3, negative 1. 9, negative 2. So this would be my graph. So the last part then to look at would be the minus 1. So what does the minus 1 do to the equation? So we did the negative log base 3 of x. We did that part, but now we have to talk about the minus 1. Virginia, what does that minus 1 do to the equation?
Would that move it, right one? Oh, down one.
So which one is it and why?
It would be down one because it does not have the parentheses.
Right, so this moves the graph down 1, and she explained it exactly correct. So there's no parentheses around the x and the minus 1. Whereas in letter A, there's parentheses with the x plus 2. So if there's parentheses, that associates it with x. It's connected with x. If there aren't parentheses, it's separate from x. And when it's separate from x, that's moving your graph up or down. So this graph, you're going to take all of your points and shift them all down 1. So each point moves down 1. It's not moving left, it's not moving right, because there aren't parentheses attached to x. So the new graph should look exactly the same. It just has shifted down 1. Does anybody know what the domain would be? Paige?
0, infinity.
Yeah, so the domain is still 0 to infinity because it's not moving left or right. It just moved down. And then Paige, the range is negative infinity to positive infinity. Every range will be the same for the log. It'll always be negative infinity to positive infinity. Good question, Lisa. All right, so do you have one other one you'd like to go over, or are we good? If there's another one, I'll take another question. Grace?
It's number 4F.
So 4f says log base 5 of 25 minus 4 and then log base 5 of the square root of 5. So Grace, the first thing I'm going to ask you is that square root of 5. How else can you write the square root of 5? Yeah, so that becomes 5 to the 1/2. So the square root is really 5 to the 1/2. This wants you to condense it to a single logarithm. So if we're condensing it to a single logarithm, what else would we do with the problem to try and condense it? Caitlin?
You would put the 4 in the
Yeah, you would take the 4 and write it as an exponent as well. So this would become log base 5 of 5. There's a 1/2, and then there's a 4 with it. Those are getting multiplied. So there's already a 1/2 there. If you're putting an extra exponent with it, you're multiplying that 1/2 with the extra exponent. So Caitlin, what does that become when you multiply those together?
5 squared.
Yeah, so that becomes 5 squared, which is 25. So this here is really saying you have 5 squared, which is 25. So if you have the log base 5 of 25 minus the log base 5 of 25, what does that equal? Why does it equal 0? It's the same thing being subtracted by the exact same thing. So that's 0. Caitlin? Or I'm sorry, Kate.
Here, so whenever subtraction really means division, so why wouldn't we divide that and have it
You
1?
could. Okay, so she said, why wouldn't we divide it and have it 1? You could divide it and make it 1. But if you think about this as an exponent, how would you write that as an exponent if I set it equal to x?
5 to the x equals 1.
What power of 5 would make it equal
0.
Yeah. No, it isn't. That's like you're thinking. That's totally correct. But because they're exactly the same, you don't have to divide them. Now, if one was a 15 and the other one was a 25, then yes. But they're exactly the same log. So if you have 5 minus 5, they're 0. If you have the log of 5 minus the log of 5, they're still the same. It gets 0. Is that?
If you get log base 5 of 5, does that also equal 0?
So she said if you have log base 5 of 5, does that also equal 0? So can you write it, anytime you're wondering, can it be changed, write it as an exponent, because it makes more sense when you think of it in an exponent.
Okay, x equals 5 to the 5th.
So 5 to the x is equal to 5. So what would your exponent be then?
1.
1.
So no.
So it would be equal to 1.
So it'd be wrong.
It's not 0. Yes.
Oh, okay. Sorry.
Other questions? Jen?
Could you write it just as log base 5 because that would be like the condensed log, or would you have to write 0?
It is 0. Like it is 0. So yes, it should be 0. Okay, so if you could place your name on that and pass it forward. I think today is pretty straightforward because it's dealing with exponents, and I think exponents are a little more easily thought of. You kind of think about them a little easier than trying to think of all this log stuff. So today, tomorrow, Friday, we're going to be solving equations, whether it's an equation involving an exponent or an equation involving a log. Today we're going to look at the exponent equations. Tomorrow we'll do the log equations. They kind of involve each other because if you have an exponent, you can make a log. If you have a log, you can make an exponent. So this should be the second to last page in your packet. I believe it's page 21. So the general forms, the conversion. See if you can write those two conversions underneath where it says the general form, exponential versus logarithmic. So we're going to solve exponential equations today. What are those general forms? So think about, what does the exponential form look like? What is its, sorry, no, I'm sorry. What does the log form look like? Ethan, what's the exponential form look like? I'll help you out. Y equals? Right, so I'm just going to take out the a and just make it y equals b to the x. So that would be our exponential form, y equals b to the x.
I would say logarithmic.
The logarithmic form, Mason, is?
Log b, y.
Right, log b, y equals x. So those are the two forms that we've been working with, converting back and forth from one to the other. So today, we're going to focus on the exponential form and see if we can try and solve the equations involving exponents. So there's a little property underneath here. I sounds like geometry with all those like postulates and theorems, but every once in a while we have to have a little property to talk about so that we can work through it. And algebra usually is properties, not like postulates and theorems. So that makes it a little better too because it says property, right? A different P word instead of postulate. So property of equality for exponential equations. So what this says in algebra, if b is a positive number, remember b is our base, other than 1, then the base with the exponent of x can be equal to the base with an exponent of y if and only if we could set x equal to y. The key thing is that the base must be the same. So if the base is the same, then we can make the exponents, exponents equal to each other. I wanted to say equal, but I knew there was another e word. So in the example underneath, we have 5 to the x is equal to 5 to the 4th. So if I want x to be 4, then I would have 5 to the 4th is equal to 5 to the 4th. My equation would be equivalent. So if I look at the exponents, whatever it takes to make them the same would then give me the same value if the base is the same, because 5 to the 4th is going to be equal to 5 to the 4th. So obviously it's not that basic, but that's essentially what we're doing. So if the bases match up, we can solve for the exponents by just setting them equal to each other. So there are 4 examples underneath here that says to solve the following by equating exponents. So that means our goal is to get the exponents to be equal to each other. But in order for that to happen, the bases have to be the same. So if you look at A, it says 64 to the x equals 16 to the x plus 1. The bases are not the same. One's a 16, the other one's a 64. So for this property to work for us, the bases have to be the same. How can you make them the same? Kate?
You could write 64 as 4 cubed, and 16 is 4 squared.
So working with exponents, we've been trying to change numbers and write them with the same bases, write them in exponential form. And that's what you're going to do with these problems. So can you take the numbers that they give you and change it so that it's as an exponent? So the 64 still has an x. The 16 had an x plus 1. So 64 is 4 cubed, 16 is 4 squared. If you have that common power sheet and that helps you change the bases, feel free to continue to use that. Because the bases are the same, we're now allowed to take the exponents and solve for them. So this exponent here is 3x because you're multiplying the exponents when you have a power to a power. What does the exponent on the right side become? Virginia?
Is it x plus 2?
You're close.
Oh, 2x plus 2.
It would be 2x plus 2. So these still get multiplied. That 2 has to go to both parts, the x and the plus 1. All of it's being raised to both of those powers, so it needs to make sure you're multiplying. And then you solve the little equation for x. So there aren't any squared terms in here. You just have 3x equals 2x plus 2. So subtract 2x, and now you get x equals 2. So just to make sure that it works, does somebody have a calculator out? Kate does. So if we plug in a 2 here, so 64 squared, is that equal to 16, which would be cubed, because 2 plus 1 makes 3. So is 64 squared equal to 16 cubed? And if you plug it in your calculator, they are equal. So it does work by getting those bases the same and then solving for the exponents. Questions? So if you look at letter B, this one has a fraction, evil fractions. 4 to the x is equal to 1/2 to the x minus 3. So your goal is to make the bases the same. Like in letter A, we made them both into 4. Virginia, what do you think?
The 1/2 to 4 to the negative 2.
This guy here? So you want to make it 4 to the negative 2. Is that the same value? So if you flip it, you get 1/4, but that 1/4 is squared. So I think you're on the right track. Like you're thinking about doing something with that fraction. Sarah?
Wouldn't you make 1/2 the -2?
For which one?
1/2.
So you guys, like you want to do something with the 1/2. 1/2 is equal to 2 to what power? To the negative 1. Is that what you said?
I said -2.
Okay. So 1/2 is really 2 to the negative 1. I can't change the value of that. So you're not allowed to make it a different value. It's just rewriting it. So 1/2 is 2 to the negative 1. But if you make that 4 to the negative 2, Virginia, that makes it 1/4 squared, which is 1/16. What could we do with the 4? It
2 squared.
is 2 squared. So when you have a fraction, remember to get the fraction to be a whole number, it has to have a negative exponent. But the exponent is just -1. So it's not going to be a squared value or anything like that. It's just like 2 to the negative 1 is 1/2. They're equal. They're the same. We just write them differently. So now we have 2 squared, 2 to the negative 1. My bases are the same, so we can then take this equation and solve for the exponents. So Ryan, this here is 2x on the left. What's the right become?
The right becomes -x + 3.
Awesome, -x + 3. So the exponent has to go to both parts, that x and the -3. So this makes 3x equals 3, so now x is equal to 1. So 4 to the first is equal to 1/2. And then the x minus 3 would be a -2. And 1/2 to the -2 is 4. So why don't you try C and D, which are pretty much the same thing as the ones above. So work through C and D, try and rewrite the bases so that they're the same, so that we can equate the exponents. Maddie, how can we change the 9
Make it 3 squared.
and 27 is?
32.
So what's our equation then?
4x equals 3x minus 3.
And x is equal to?
-3.
Good, -3. So just plugging it in up here, that would give us 2 to the -6, or 9 to the -6, and 27 to the -4. And again, if you plug them in and check it, you can always check to see if your values are correct, making sure that they're equivalent. Letter D, what would we change 81 to? Yeah, 81 is 3 to the 4th. That common power sheet might be pretty helpful. And then 1/3 is really 3 to the -1. So our equation becomes nice. Just be careful, that 4 goes to both pieces as the -1 goes to both pieces. So if we take the 5 to the left, that would give us a positive 1x. And if we subtract 12, that gives us a -6. Any questions with equating exponents? Pretty straightforward, hopefully. So if you flip the page, we're still going to work with exponents, but instead of having 2 exponents equal to each other, there are other equations that involve exponents that can be set up differently. So the 4 problems over here, there's one exponent, and then we have other numbers being added, subtracted, multiplied with the equation, but there aren't two exponents for us to set equal to each other. So the directions here say solve the following by taking a logarithm of each side. So what that means is that you currently have the exponential form. In order to solve it, we're going to have to create the logarithm form. So in letter A, we have 6 to the x is equal to 27. 6 to the first is 6. 6 squared is 36. So the answer has to be between 1 and 2, but there's no way for us to find out that answer as it's written as an exponent, which is why the logarithm was created. So the only way we can solve this problem in exponential form would be to rewrite it and try and solve it as a log. So how would this equation be written in log form? Ethan?
Log base 6, 27.
Yeah. So now, using that handy-dandy calculator, either using the math and then scrolling down to A because you have that function in your calculator, or if you don't have that function in the calculator, you have to take the log of 27 divided by the log of 6, because that's what the calculator is really doing when you press that button. That's what my solution would be equal to. So if you have the button in your calculator, awesome. If not, it's okay. You can still solve it. You're just using the log button on the side of the calculator. Ethan, do you have an answer? How about 3 decimal places?
1.34.
One more?
1.344.
So we knew it had to be between 1 and 2 because 6 to the first is just 6. 6 squared is 36. So 6 to the 1.344 would be approximately. You got something different?
What I do wrong?
I don't know. What did you get, Virginia?
I got 1.839.
839.
Oh, that is what I got. That's right.
Anthony, did he really get that?
Hey, I got that. I don't know why.
Why didn't you?
Okay, so 1.839. That sounds a little better. Questions on the letter A?
I don't know why.
Okay, so if you look at letter B, looks a little different than A because, well, there's an E in it, but there's also a 6 in front. There's a plus 8 behind it. There's an exponent that has a 0.25 with it, so a little more interesting than just 6 to the x equals 27. But think back to all the equations that we've solved. Sarah, what do you think you'd have to do first?
Subtract the 8.
Right, subtract the 8. So what is the goal by subtracting 8, Sarah?
Getting the e by itself.
Right, we're going to get the exponent by itself. So in A, it was already by itself. We didn't have to do anything extra with that. In letter B, we have to get it by itself. So what else would we have to do? Right, divide by 6. So now e to the 0.25x is equal to 2. Now, the exponent part, you can't do anything with that. That 0.25 has to stay with the exponent. But right now, the e is by itself. So when you have an e, what form do you convert e to? David? ln. So what would it look like, David, if we're converting it to the natural log? So ln of 2 is equal to 0.25x. Remember, you don't have to write the base there. Now, before you put this in your calculator, because I don't want you rounding twice, I want it rounded once, get x by itself. So how would you get x by itself, David? Right, divide by 0.25. So in your calculator, you're going to take the ln of 2, and then you're going to divide that by 0.25. I thought my calculator was up. So don't take 2 divided by 0.25 because that's not what it's saying. It's saying the natural log of 2 and then divided by 0.25. So David, what did you get? 2.773. Anybody not get that? So again, you're taking the ln of 2, then dividing it by 0.25. Just make sure you end the parenthesis around the 2. So the last two problems are exactly like the ones above them. Number 5 said, or letter C says 5 to the x is equal to 72. So Maddie, what we do with that one?
Log boost 5, 72 equals x.
And then plug that in your calculator. Depending on your model, you're either taking the log of 72 divided by the log of 5, or you're just using that fancy button in your calculator. Grace, what do you have?
X equals 2.657.
And then the last problem, 4e to the negative 0.3 minus 7 equals 13. So Mason, what will we do to solve letter E?
Add 7 to the other side.
So 4e to the negative 0.3x is equal to 20, and then
ln is equal to negative 0.3x.
so he said ln of 4 about 5 is equal to negative 0.3x. So you take the natural log of 5, divide it by negative 0.3, and that should be equal to x. What do you have, Mason?
Negative 5.365.
Are there questions with solving exponential equations with the bases being the same, equating the exponents, or changing it to log form and solving it? So your homework is 1 to 23 odd. The book is open, it's the bottom of the first page and then the top of the second. It's all exponential equations, exactly like we did. They're broken up exactly like they've been broken up in the notes. How about somebody do 9? Jenna? 23, Maddie?
Yes. I'm the only one in this class. I didn't know there was another Maddie.
Yeah,
There's
that
not.
was
I really don't like
that.
Say my homie Nixie. I love you, Nick.